Hi, everybody. I will be working on a problem by request. So let's get started. This is section 2.1, exercise 3. The problem's written big here. What we need to do is, well, prove that T is a linear transformation. Find bases for both n of T, that's the null space of T, and R of T, the range of T. Then compute the nullity and rank of T and verify the dimension theorem. Finally, use the appropriate theorems in this section to determine whether T is one-to-one or onto. All right, so let's look at number 3. T from R2 to R3, defined by T of a vector A1, A2, equal to a three-dimensional vector A1 plus A2, comma 0, comma 2A1 minus A2. Now the problem's going to get a little bit smaller as we make room to write. All right, so first let's just observe that T is in fact linear. So in order to do that, we need to apply the transformation T, I should say the function T, until we know that it's a linear transformation, to a sum of vectors. So in this case, A1, A2, and then B1, B2, and we'll add those together. Well, first I should add those together. So we'll get a single vector with two components. The first component will be A1 plus B1. The second component will be A2 plus B2. And now I know what T does to a two-component vector like this. The first component is the sum of the two components. So I'll get A1 plus B1 plus A2 plus B2. Then the second component will be 0 no matter what. And whoops. The third component will be twice the first component. So that is 2 times the quantity A1 plus B1. Then minus the second component, which is A2 plus B2. All right, and now let's just observe that we could split this up into really a sum of two vectors that only involve A's and B's. So I'll write this as A1 plus A2, comma 0, comma distributing out. This will be a 2A1 minus A2. And then also I will have a B1 plus B2, and then a 0, and then a 2B1 minus B2. Let's just double check that everything's there. I've got a 2A1 and a 2B2, 2A1 and a 2B1. I've got a minus A2 and a minus B2. And yeah, that looks right. If you check this out, the sum of these two vectors will in fact exactly be the vector above. And then it's fairly straightforward to realize or recognize that this is T of A1, A2, and that this is T of B1, B2. So yes, in fact, T preserves or respects addition. Similarly, if we were to take C times the vector A1, A2, and then apply T, well, first I should write this as a two-component vector, CA1, CA2, then apply T. Well, that should give me the sum of these two guys, CA1 plus CA2, comma 0, and then finally 2 times the first component, CA1, minus the second component, which is CA2. And let's recognize that we can in fact factor a C out from everything in this vector, including the 0. And what we're left with is precisely C times T applied to the vector A1, A2. Great, so this verifies T is a linear transformation. So far, so good. We have accomplished the first line of the exercise. All right, the next goal is to find bases for both the null space and the range of T. So let's start with the null space. Let's see, what is the null space? Recall, the null space of a linear transformation T is the set of all vectors from the domain with the property that T applied to that vector results in the zero vector in the codomain. So in this case, well, the domain is R2, so that will be vectors in R2 of this form, satisfying the condition that T of them, or T of it, is equal to the zero vector in R3. Well, that's just a 3-tuple of zeros. All right, so what does it mean that T of A1, A2 is equal to 0, 0, 0? Well, T of an arbitrary A1, A2, well, we know the formula for T. That's going to be A1 plus A2, and then 0, and then 2A1 minus A2. So if this is supposed to equal 0, 0, 0, this would imply that, in particular, the first component, A1 plus A2, is equal to 0, and 2A1 minus A2 is equal to 0. Well, this is a system of equations now involving A1 and A2. So, for instance, we could add these two equations together and find that 3A1 plus 0 has to equal 0, which then implies that A1 must, in fact, be 0. And if A1 must be 0, then using either of these two original equations, we can find that A2 would have to be 0 as well. So now what we've done is shown that not only is 0, 0 one of the things in the null space of T, but if any vector is in the null space of T, it must be the vector 0, 0. So what we've really shown is that the null space of T in this particular example is just the set containing the 0 vector, and that's the trivial, or the 0 vector space. So a basis for n of T is the empty set, because we gave as a special condition that we could call the empty set a basis for the 0 vector space. All right, so far so good. Now we've got the null space. We figured out what the null space is, and we found a basis for it. So now let's look at the range of T. So the range of T is equal to the set of all W's from the codomain, satisfying the condition that there exists a V in the domain that T sends onto that particular W. Okay, here's another way of writing exactly the same thing. Instead of naming abstract-looking vectors from the codomain, let's say that every vector in the range has to be T of V for some V in the domain. And now if we let V range over all the vectors in the domain, then T of those will give us the collection of all the things in the range. All right, so in this case, this means it's the set of all T of A1, A2. Let's write that a little bit neater. A1, A2, so that A1, A2 is in R2. Oh, well, we can actually just write that down exactly, because we know what T of A1, A2 is. That's the set of all three vectors of the form A1 plus A2, 0, 2A1 minus A2, where A1 and A2 are allowed to be really any pair of real numbers, or in other words, A1, A2 is allowed to be any vector from R2. So that is the range here. How do we find a basis for the range? Well, there's a theorem that we will be discussing in class, and it's in the book. And it says that the span of T of a basis is equal to the range of T for a basis beta for the domain V. I guess the setting here, let's say that T is a linear transformation. All right, so in other words, if I took a basis for the domain, applied T to each of those vectors, then at the very least, I get a set of vectors that span the range. All right, so can we think of our domain here is R2? Can we find a basis for R2? Oh, I guess we could just use the standard basis. 1, 0, and 0, 1. So what this theorem tells us then is that T of beta, well, that's T of 1, 0 and T of 0, 1, that this spans the range of T. Not that it's a basis. The theorem does not say that you get a basis for the range of T. It just says that you span, the span of those vectors is equal to the range of T. All right, but that's a start because a basis has to span and be linearly independent. So at least we get something that spans. So, okay, what is T of 1, 0? Well, we know what T does. It does that. So let's see, T of 1, 0 is just going to be 1 and then 0 and then 2. Okay, similarly, we could apply T to 0, 1, and we're going to get, 0 plus 1 is 1, and 0, and 0 minus 1, that's a minus 1. Great, so this is a set that spans the range of our linear transformation. And now a quick inspection will let us see. Notice in this case, these vectors are already linearly independent. This is a linearly independent set. Okay, so if we have a set of vectors that spans the range and it is linearly independent, then we have a basis. So the set containing the two vectors, 1, 0, 2, and 1, 0, negative 1, is a basis for R of T. Whew. Okay, so what have we got now? We showed that T was a linear transformation. We found bases for the null space and the range of T. So we want to compute now the nullity and the rank of T, verify the dimension theorem. Well, nullity of T is just the dimension of the null space of T, which is the number of vectors in a basis for n of T. But we said the basis for the null space here was the empty set, so there are no vectors in that basis, so the nullity of T is 0 in this particular case. Similarly, the rank of T, well, that's just the dimension of the range of T. That's the number of vectors in a basis for R of T. And we found a basis over here. It's got 2 vectors in it, so the dimension must be 2. Finally, let's look at the dimension theorem. The dimension theorem says that the dimension of the domain of a linear transformation T is equal to the dimension of the null space, or the nullity, plus the dimension of the range of T, or in other words, the rank of T. So in this case, the domain, that's R2, so we know that it has dimension 2. The null space had dimension 0, so the nullity was 0. And the dimension of the range, that's the rank of T, that was 2. So yes, in fact, 2 does equal 0 plus 2. So that's very nice. Finally, we can use the appropriate theorems to determine whether T is 1-to-1 or onto. Well, there's an important theorem which says T is 1-to-1 if the null space of T is equal to only the 0 vector. But in this case, that's true. In this case, the null space of T is equal to only the vector containing 0, 0 in R2, which is the 0 vector. So T is 1-to-1. And finally, in order to be onto, we would need that the range of T was equal to all of R3. But we know that that can't be the case because the range of T has dimension 2, while the codomain R3 has dimension 3. So the range of T does not equal R3, and T is not onto. Close that so that becomes visible on the page. The range of T has dimension 2, while the codomain R3 has dimension 3. So the range of T is not equal to R3, and we know that T is not an onto function. So it is 1-to-1, it is not onto. I believe we've now answered all of the questions. Hopefully that was helpful. Please feel free to ask any follow-up questions, and hopefully you find these examples helpful, and I will continue to do them in the future.